Welcome students. Today I will discuss very briefly about the electrical energy and electrical power which the students of various boards may find helpful. Let us start with the electrical energy. So students, from the definition of potential difference, we know the work done in moving a charge of amount Q through a potential difference V is Q into V. So work done in this case, if denoted by W, then W equal to Q into V. This work in a closed circuit is done by a source, that is a battery or the AC mains. So the battery or the AC mains actually supplying the energy into the circuit, which in turn results in current. As we know, the movement of charge causes current. Let us consider that this movement of the charge Q for the time t results in current I. Then Q equal to I multiplied by T. Then from the electrical energy or the work done relation we have, after putting the value of Q as IT, W equal to ITV. On rearranging, we have W equal to VIT. So we have a equation of electrical work or electrical energy being expressed in terms of the voltage, the current and the time for which the current is been flowing. Let us now find different form of equation for the electrical energy. As we have W equal to VIT, and from Ohm's law we know voltage is the product of the current flowing and the resistance of the conductor, that is V equal to IR. Now putting this value of the voltage V, that is equal to IR, into the equation of the work done, we have W equal to IR into IT, or simply W equal to I square RT. Let us now find another form of equation of electrical energy. Initially we had W equal to I square RT, and from Ohm's law we know V equal to IR, or the current I is simply V by R. Putting this value of I, we get W equal to V square T by R. So W equal to V square T by R is another form of the same equation which relates V and R with the electrical energy. Let us now finally find the third form of this electric energy equation. Again, initially we had W equal to I square RT, and from Ohm's law V equal to IR. Now replacing the resistance R, we have R equal to V by I. So the equation reduces to W equal to VIT, which is another form of electrical energy which now relates voltage, current and the time with the electrical energy. So finally, the three forms of the electrical energy we have are W equal to I square RT, then W equal to V square T by R, and finally W equal to VIT. They all represent the same physical quantity, that is the electrical work or the electrical energy. Let us now see what electrical power is all about. Well, the classical definition of power in physics is the time rate of doing work. In case of electrical power, it is the time rate of expending electrical energy. Electrical power is normally conferred upon electrical appliances which run by consuming electrical energy supplied by sources such as AC mains or battery. For an appliance such as this one, the power means the rate at which it's consuming electrical energy supplied by the mains at our home, irrespective of its work output. So power is actually energy divided by time. Hence electrical power is the electrical energy divided by time, and the SI unit being watt. It's easy to find how to calculate power once you know different forms of electrical energy equation. We know electrical energy represented by W equal to I square RT. Corresponding power equation will be just dividing it by T, I square R. For electrical energy of the form V square T by R, the corresponding power equation will be V square by R. And finally, for W equal to VIT, the power will be VI, just devoid of T. Let us now see some bigger units of power. We have 1 kilowatt, often written as shown in the figure, is actually 1000 times a watt, that is 10 to the power 3 watt. Then 1 megawatt is 1000 times a kilowatt, that is 10 to the power 6 watt. And 1 gigawatt is 1000 times a megawatt, that is 10 to the power 9 watt. Let us now see the electrical energy units being used for commercial purposes. Well, electrical power is electrical energy divided by time, or power represented by P is equal to energy represented by E divided by time T, or energy E equal to power P into time T. It means electrical energy can be deduced by simply multiplying power unit and time unit. That is, unit of power multiplied by unit of time is equal to unit of electrical energy. Let us now put watt in place of power and seconds in place of time. This product is also a unit of energy. Let us now replace second by hour, then the product of watt and hour is also a unit of electrical energy. Finally, replacing kilowatt instead of watt multiplied by hour will also give rise a unit of electrical energy. Thus, kilowatt hour is a much utilized commercial unit of electrical energy. All the household billing of AC sources and the industrial billing also, the billing is done on basis of the unit kilowatt hour. Let us now find the relation between kilowatt hour and its smaller counterpart joule. Well, kilowatt hour, which is actually some amount of electrical energy, must have the same dimension as that of joule. Then 1 kilowatt hour is equal to 1000 watt if you debit the term kilo and multiplied by 3600 seconds if hour is replaced by second. Then we have 1 kilowatt hour equal to 3.6 million watt second. That is 3.6 million joule, as watt second has the dimension of joule. Therefore, 1 kilowatt hour is 3.6 million joule, or 3.6 into 10 to the power 6 joule. Let us now discuss power ratings of appliances. For this, let us consider a bulb has a rating 100 watt and 220 volt written on it. Now what does that mean to? It means the bulb, once connected to 220 volt mains, will dissipate electrical energy at a rate of 100 joule per second, and the luminosity of the bulb thus will be maximum. Let us take that very instance for the following numerical problem. A bulb with rating 100 watt 220 volt written on it, what will be its resistance and safe current? Well, we have P, that is the power, equal to 100 watt, voltage V equal to 220 volt, and we know P equal to V square by R, which relates power with voltage and resistance. Therefore, resistance R equal to V square by P, that is 220 whole square divided by 100 ohms, which is nearly 484 ohms. This resistance is so chosen that when the bulb connected across 220 volt mains, its power consumption becomes 100 watt. And the safe current I equal to V by R according to Ohm's formula. That is 220 divided by 484 ampere. That is nearly equal to 0.45 ampere. This current is called safe current in the sense that if the mains supplies current more than 0.45 ampere and the fuse or the MCBs do not respond in time, the bulb filament will not be able to withstand that current and will get torn apart due to heating. Dear student, that's all for now. Hope you will find it helpful. Thanks for watching and listening.